time may not be endlessly divisible. There may exist a scale where cutting a second any further stops revealing detail and starts exposing a hard boundary built into nature itself. That boundary has a name: Planck time. About 5.39 times 10, -44 seconds, defined as the interval light needs to cross 1 Planck length. Below this scale, the two frameworks that describe reality best, quantum mechanics and gravity, no longer align, and even the idea of a measurable duration begins to lose stability. This story traces how time moved from heartbeats and mechanical clocks to atomic oscillations, why light quietly governs every precise measurement, and how modern experiments have reached attoseconds, while still remaining unimaginably far from the Planck scale. What emerges is not a mystery for its own sake, but a boundary revealed by real constants and real limits. That boundary brings us directly into part 1. Is there a shortest possible moment where time itself stops making sense? Planck time emerges from 3 constants that appear everywhere in modern physics: the speed of light, c, the gravitational constant, g, and Planck's constant, These are not human inventions. They are measured properties of the universe. When combined mathematically, they produce a natural unit of time that does not depend on clocks, observers, or conventions. It depends only on how space, energy, and gravity behave. This construction was first outlined at the end of the 19th century by Max Planck, who recognized that these constants defined natural scales of length, time, and mass. At the time, these quantities seemed abstract. No experiment could reach them. But a century later, they began to look less like mathematical curiosities and more like warning signs. Planck time can be described simply. It is the time required for light, traveling in vacuum, to cross 1 Planck length, about 1.62 times 10, -35 meters. That distance is not small in a familiar sense. It is small in a categorical sense. Below it, the concepts of distance and duration stop behaving as separable ideas. Richard Feynman once summarized this tension with a blunt observation: "Nature isn't classical, damn it." His remark was not rhetorical. Classical physics assumes that time and space can be divided without limit. Quantum mechanics, however, introduces uncertainty. Gravity, described by general relativity, introduces curvature. At everyday scales, these effects can be ignored. Near the Planck scale, they collide. This collision creates a problem that no existing theory resolves. Quantum mechanics works extremely well at small scales, accurately predicting the behavior of particles and fields. General relativity works extremely well at large scales, accurately predicting the motion of planets, stars, and galaxies. But when both are required at once, when energy densities approach extreme values over extremely small intervals, neither theory remains reliable. Physicists do not say that time ends at Planck time. What they say is more careful and more unsettling. Below this scale, the equations no longer produce testable predictions. It is not that events stop happening. It is that our language for describing events loses coherence. Historical experiments underline how far removed this boundary is from anything humans can directly observe. In the early 20th century, researchers first measured radioactive decay times on the scale of seconds and minutes. Later, particle accelerators revealed lifetimes measured in microseconds and nanoseconds. Muons, for example, decay in about 2.2 microseconds when at rest, a value confirmed repeatedly in laboratories around the world. As accelerator technology improved, even shorter intervals entered experimental reach. The tau lepton, discovered in the 1970s, decays in roughly 2.9 times 10, negative 13 seconds. These measurements were not theoretical guesses. They were confirmed through detectors, timing, electronics, and repeated observation. In the 21st century, laser physics opened another window. Techniques developed by researchers such as Stephen Chu and others allowed the creation of pulses lasting attoseconds. 10, negative 18 seconds. Short enough to observe electron motion within atoms. In 2020, experiments at facilities such as DESI in Germany measured processes lasting only a few zeptoseconds, 10, negative 21 seconds, by tracking how photons interact with atomic nuclei. These achievements are remarkable. Yet even zeptoseconds remain separated from Planck time by more than 20 orders of magnitude. This gap is not one of engineering alone. It is structural. The deeper physicists probed, the clearer it became that Planck time is not merely a very short duration. It represents a change in regime. At this scale, energy concentrated into a region small enough would curve space-time so strongly that the act of measurement would disrupt the phenomenon being measured. Any attempt to localize an event more precisely would require energies that, according to general relativity, would form a microscopic black hole. This reasoning does not depend on speculative physics. It follows directly from established equations. Combine the uncertainty principle with Einstein's field equations, and the result is unavoidable. Below a certain scale, space-time cannot be treated as a smooth background. John Wheeler described this breakdown with a phrase that remains influential: quantum foam. He was not suggesting turbulence in a fluid sense. He was pointing to a regime where space-time geometry itself fluctuates unpredictably, where notions such as before and after lose their ordinary meaning. NASA and ESA research programs continue to explore the early universe precisely because traces of this regime may be indirectly accessible. Observations of the cosmic microwave background, measured by missions such as WMAP and Planck, reveal temperature fluctuations that encode information from when the universe was about 380,000 years old. These measurements confirm predictions made by quantum field theory in curved spacetime, but they also hint at physics beyond current models. More recently, the James Webb Space Telescope has observed galaxies forming earlier and more rapidly than many models predicted. These findings do not contradict Planck-scale physics directly, but they sharpen the need for a theory that consistently links gravity and quantum behavior from the earliest moments onward. What makes Planck time particularly compelling is that it is not chosen for convenience. A second can be defined many ways. Planck time cannot. Change its value, and the constants of nature would no longer agree with observed reality. This is why physicists describe Planck time as a boundary rather than a target. It is not something experiments are expected to reach. It is something theories must respect. Any successful theory of quantum gravity, whether loop quantum gravity, string theory, or another framework yet to be developed, must reproduce known physics above this scale, while explaining why description fails below it. There is no drama in this conclusion, only discipline. Physics does not claim that reality disappears at Planck time. It claims that our present tools stop working there. That distinction matters. It preserves what science does best, stating clearly what is known, what is measured, and where explanation remains incomplete. The smallest meaningful unit of time, then, is not a tick on a clock. It is a signal that the universe has limits built into its structure. limits that no refinement of technique can bypass. Without new principles. At that boundary, a quiet inconsistency appears. If nature itself refuses to define intervals shorter than Planck time, then the second we rely on every day cannot be as absolute as it seems. Part 2. Why isn't a second as solid as we think it is? If a second were defined by your heartbeat, the universe you measure would slow down when you rest and speed up when you run. That simple fact exposes something deeply unsettling. The second you trust every day is not a property of nature itself, but a human construction layered on top of biological rhythms, mechanical convenience, and technological negotiation. For most of human history, time was not something measured with precision. It was observed. Days were marked by sunrise and sunset. Seasons were tracked by shadows and stars. A second did not exist as a concept. What existed were intervals tied to living bodies and visible motion. A blink, a breath, a step. Even today, your nervous system still treats time this way. Reaction times cluster around tenths of a second. Visual perception blends events separated by a few milliseconds into a single experience. Biology smooths time automatically. The first attempts to standardize smaller units came from mechanics, not physics. Early pendulum clocks in the 17th century, developed by Christian Huygens, divided the day into increasingly smaller segments using regular motion. The swing of a pendulum became a reference because it was repeatable, not because it was fundamental. Change the length of the pendulum, and the timekeeping changed. Temperature, air pressure, and gravity all affected it. The second was already negotiable, even then. As navigation and astronomy advanced, this flexibility became a problem. Determining longitude at sea required precise time comparison between a ship and a reference meridian. In the 18th century, John Harrison's marine chronometers solved this practical crisis by maintaining stable oscillations aboard moving ships. These clocks were engineering triumphs, but they did not redefine what time was. They only improved consistency. The modern second emerged much later, when physics demanded something more stable than any mechanical system. By the mid-20th century, scientists realized that Earth itself was an unreliable clock. Its rotation is not perfectly uniform. Tidal interactions with the moon, redistribution of mass in the oceans, earthquakes, and even atmospheric circulation subtly alter the length of a day. Measurements by observatories showed that Earth's spin slows by about 2 milliseconds per century. Small, but measurable. This forced a shift away from astronomical time toward atomic time. In 1967, the General Conference on Weights and Measures adopted a new definition of the second based on the behavior of atoms. 1 second was defined as a specific number of oscillations of radiation emitted by cesium-133 atoms under controlled conditions. The choice was not arbitrary. Cesium atoms oscillate with extraordinary regularity, unaffected by temperature or mechanical wear, in the same way as physical devices. This definition is still in use today. It anchors global timekeeping systems, including GPS satellites operated by agencies such as NASA. These satellites carry atomic clocks that must account for both special and general relativity. Because the satellites move rapidly and reside in weaker gravitational fields than clocks on Earth's surface, their time runs faster by about 38 microseconds per day. Without correcting for this effect, GPS positioning errors would accumulate by several kilometers each day. This correction alone demonstrates something critical. A second does not flow universally. It depends on motion and gravity. Einstein expressed this operationally, not philosophically. Time, he emphasized, is what clocks measure, and different clocks, following different paths through spacetime, do not agree. The deeper scientists looked, the clearer it became that the second is a convention designed to remain useful across contexts, not a fundamental slice of reality. Atomic clocks provide remarkable stability, but even they are subject to limits. Their precision relies on averaging vast numbers of atomic transitions. What feels continuous is, in practice, statistical smoothing. Experiments at institutions such as NIST in the United States and ESA-supported laboratories in Europe have pushed time measurement to extraordinary precision. Optical lattice clocks now achieve accuracies where differences in gravitational potential across a vertical distance of less than 1 meter cause measurable time dilation. Raise a clock slightly, and it ticks faster. This is not a theoretical prediction. It has been observed. At these levels, the second becomes fragile. It stretches and compresses depending on where and how it is measured. The illusion of solidity persists only because everyday differences are too small for human perception. Biology averages them away. History provides a useful contrast. When early psychologists studied human perception of time in the late 19th century, they found that perceived duration varies dramatically, with attention, emotion, and fatigue. A second during danger does not feel like a second during rest. These findings were not errors. They reflected how the brain constructs time internally. Physics, by contrast, had to strip away perception entirely to build a usable standard. This separation between lived time and measured time is where confusion often arises. People assume that because a second is precisely defined, it must be fundamental. In reality, it is optimized. It is chosen to align with atomic behavior because atoms offer stability, not because the universe recognizes seconds as meaningful units. As measurements shrink further, this distinction becomes unavoidable. Ultra-fast laser experiments measure processes lasting femtoseconds and attoseconds. These intervals are not subdivisions of seconds in a physical sense. They are ranges where entirely different behaviors dominate. Electron motion inside atoms unfolds on these scales. Chemical bonds form and break within them. Time here is inferred from interaction, not counted by ticks. NASA-supported research into ultra-fast dynamics, combined with ESA-backed facilities, has shown that as intervals shorten, the notion of a clean temporal boundary dissolves. Events overlap. Cause and effect blur slightly, not because physics fails, but because measurement relies on averaging interactions across ensembles. This trend continues until the concept of a second loses relevance altogether. Long before reaching Planck time, seconds cease to be meaningful descriptors. They are too large, too coarse. Physics does not protest loudly. It simply stops using them. The story of the second, then, is not about discovery of a natural unit. It is about convergence. Biology provided rhythms. Mechanics provided regularity. Astronomy provided scale. Atomic physics provided stability. Relativity provided correction. The second survived because it adapted. Carl Sagan once described science as a way of distilling truth from confusion. In timekeeping, that distillation required abandoning intuition. The second feels solid because it works, not because it reflects the universe's deepest structure. What remains remarkable is not that the second is imperfect, but that it functions as well as it does across such vast conditions. From satellites orbiting Earth to laboratories measuring atomic transitions, the second holds together a coordinated picture of motion, navigation, and communication. Yet beneath that coordination lies a quiet instability. The second is a bridge between human needs and physical behavior, not a cornerstone of reality. As measurements approach ever shorter intervals, that bridge narrows. At that narrowing, every attempt to refine time runs into the same physical fact. No signal travels faster than light. And every clock, no matter how advanced, is bound by that limit. Part 3. How does light quietly control every meaningful measure of time? Every serious attempt to understand time eventually collides with an uncomfortable fact. No matter how carefully we measure, how finely we divide, or how advanced our clocks become, the final authority is always light. When intervals shrink enough, time stops being something counted by mechanisms and becomes something enforced by a speed limit written into the structure of the universe. This realization did not arrive suddenly. It emerged slowly, through experiment, contradiction, and correction. In the late 19th century, physicists believed time flowed uniformly everywhere. Light was assumed to move through space the way sound moves through air, its speed depending on the motion of its source, or the observer. That assumption felt reasonable. It was also wrong. The first cracks appeared with precise measurements of electromagnetic waves. Experiments by Albert Michelson and Edward Morley in 1887 attempted to detect Earth's motion through a hypothetical medium called the ether by measuring changes in the speed of light along different directions. The result was not ambiguous. The speed of light remained the same, regardless of Earth's motion. No adjustment of apparatus fixed this. nature refused to cooperate with expectation. At the time, this result was deeply unsettling. If light did not behave like other waves, then either the experiments were flawed or the foundations of time and space were incomplete. Over the next 2 decades, similar results accumulated. Light's speed, measured in vacuum, appeared fixed, not approximately fixed, exactly fixed. In 1905, Albert Einstein accepted this result without compromise. He proposed that the speed of light in vacuum is the same for all observers, regardless of their motion. This was not a statement about light alone. It was a statement about time. If light's speed cannot change, then distances and durations must adjust instead. Einstein expressed this with unusual clarity. In his words, time is what a clock measures, but once clocks depend on light signals, and light obeys a universal speed limit, clocks cannot agree universally. Motion reshapes time. This insight transformed physics. Space and time, previously treated as separate, became linked. Events were no longer ordered by a single universal clock, but by their position within space-time. Cause and effect were constrained by how fast information could travel. Light was no longer just illumination. It became the rule set. Modern experiments confirm this daily. Atomic clocks, synchronized using light signals, must account for relativistic effects to maintain agreement. NASA's GPS satellites provide a clear example. Each satellite carries atomic clocks that tick slightly faster than clocks on Earth's surface, due to weaker gravity and relative motion. Engineers correct these differences using Einstein's equations, not because they admire theory, but because, without correction, navigation fails. Light governs this correction. Synchronization relies on signals exchanged at light speed. The assumption that light speed is constant underpins the entire system. Remove that assumption, and the concept of a global time reference collapses. As time intervals shrink, this dependence intensifies. Mechanical clocks rely on moving parts. Atomic clocks rely on oscillations of atoms. Optical clocks rely on transitions driven by light itself. The more precise the clock, the closer it moves toward light as its regulating mechanism. Research institutions supported by NASA, ESA, and national laboratories around the world have developed optical lattice clocks that use light trapped in standing wave patterns to hold atoms in place. These clocks measure time using transitions in atoms such as strontium and ytterbium, driven by laser light. Their precision is so high that differences in altitude of less than 1 meter produce measurable time dilation due to gravity. At this level, the second becomes inseparable from light. Timekeeping is no longer about counting cycles. It is about managing light-matter interaction with extraordinary control. This dependence explains something deeper. When physicists define Planck time, they do not reference clocks at all. They reference light. Planck time is defined as the interval required for light to travel 1 Planck length in vacuum. This is not symbolic. It reflects necessity. Below that interval, there is no operational way to define causality without violating the light speed limit. Light enforces order. It sets the maximum rate at which information can propagate. No cause can outrun it. No signal can bypass it. Time, at its most fundamental, is constrained by this limit. Observations from astronomy reinforce this perspective. When NASA and ESA observe distant galaxies using telescopes such as the Hubble Space Telescope and the James Webb Space Telescope, they do not see the universe as it is now. They see it as it was, delayed by the finite speed of light. Light carries timestamps embedded in its journey. A galaxy observed at a distance of 10 billion light-years is seen as it existed 10 billion years ago. This is not interpretation. It is geometry, enforced by light's speed. The universe presents itself layered in time because light cannot travel instantaneously. JWST's observations of early galaxies demonstrate this clearly. Some galaxies appear more massive and structured earlier than expected. These findings challenge models of galaxy formation, not because light misleads us, but because it faithfully preserves temporal order. What we see is genuinely ancient. Light also controls experimental access to small intervals. Ultra-fast laser experiments measure electron dynamics by probing systems with pulses of light lasting attoseconds. These pulses do not mark time directly. They trigger interactions whose outcomes are interpreted through light's behavior. The measurement of duration becomes an inference based on how light interacts with matter. As experiments approach shorter timescales, the role of light becomes more dominant, not less. Time is not subdivided arbitrarily. It is resolved only insofar as light can mediate cause and effect. This principle explains why every theory of quantum gravity must respect light's role. Regardless of whether spacetime is discrete or continuous, any viable theory must reproduce the observed invariance of light speed at accessible scales. This constraint shapes all proposals. Carl Sagan often emphasized how deeply connected measurement and understanding are. He wrote, "Science is a way of thinking much more than it is a body of knowledge." In the case of time, that way of thinking begins by accepting what light enforces, not what intuition prefers. Light quietly dictates which questions are meaningful. Ask how fast something happens, and the answer must account for how information travels. Ask when two events occur, and the answer depends on how signals connect them. Time is not independent. It is relational, bound to communication. This binding becomes unavoidable near fundamental limits. If one attempts to define a duration shorter than Planck time, the definition collapses. There is no operational procedure to measure it without invoking energies that disrupt spacetime itself. Light cannot probe it cleanly. Causality loses its structure. This is not failure. It is boundary recognition. Physics does not promise infinite resolution. It promises consistency, where resolution is possible. Light's role is therefore not dramatic, but decisive. It does not announce itself. It simply constrains everything quietly. Clocks adapt to it. Measurements align with it. Theories bend around it. And as this control becomes clearer, another tension comes into view. If light governs time so completely, then what happens when light itself interacts with gravity strongly enough to curve spacetime? That question does not belong to light alone. It belongs to the structure of spacetime itself. Long before Planck limits are ever approached, particles that exist only briefly already reveal that nature operates on timescales far beyond anything a clock can track. Part 4. What do short-lived particles tell us about time beyond human scales? What kind of universe allows particles to exist for less time than it takes a human brain to register a sensation, and still treats those fleeting intervals as perfectly real? That fact alone forces time out of familiar territory and into a regime where duration is not sensed, remembered, or felt, but measured through traces left behind by particles that vanish almost as soon as they appear. Long before physicists could observe such brief existences, time was understood through repetition and endurance. A pendulum swings, a planet completes an orbit, even an atomic transition repeats itself billions of times per second. These processes endure long enough to be counted. But the universe also contains events that do not repeat in that way. Some processes occur once and end, leaving only statistical patterns behind. Particle lifetimes belong to this category. The discovery of unstable particles in the 20th century transformed how time was understood at small scales. When cosmic rays were first studied in the 1930s, detectors placed high in the atmosphere and deep underground began registering unexpected signals. Particles were arriving at Earth's surface that should not have survived the journey if their lifetimes were measured the way clocks measure time. One of these particles was the muon. Muons are heavier relatives of electrons. They are produced when high-energy cosmic rays strike atoms in Earth's upper atmosphere, creating cascades of secondary particles. In laboratory conditions, a muon at rest decays into lighter particles in about 2.2 microseconds. This value has been confirmed repeatedly in particle accelerators and detectors worldwide. On human scales, this interval is extremely short. On cosmic scales, it is negligible. Yet muons created tens of kilometers above Earth's surface routinely reach detectors at ground level. They should not. Even traveling near the speed of light, a particle with such a short lifetime should decay long before completing the journey. And yet, they arrive in large numbers. The explanation was not experimental error. It was time dilation. According to special relativity, time measured in a moving system runs more slowly relative to a stationary observer. From the muon's perspective, the distance to Earth's surface is contracted. From Earth's perspective, the muon's internal clock runs slow. Both descriptions agree on one outcome. The muon survives long enough to be detected. This was not a philosophical argument. It was confirmed through counting. Detectors measured muon flux at different altitudes and compared decay rates. The results matched relativistic predictions precisely. Time at the scale of microseconds was behaving differently depending on motion. Muon experiments did something important. They demonstrated that time intervals far shorter than human perception are not abstract. They are operational. They can be measured, compared, and predicted. Time does not need to feel long to be real. As particle physics advanced, even shorter lifetimes entered experimental reach. The development of particle accelerators after the Second World War allowed physicists to create particles that do not occur naturally at Earth's surface. Among these was the tau lepton, discovered in the 1970s at the Stanford Linear Accelerator Center. The tau particle is significantly heavier than the muon and far less stable. Its average lifetime is about 2.9 times 10 to the power of -13 seconds. This is less than a trillionth of a second. No clock ticks that fast. No detector watches it decay in real time. Instead, physicists reconstruct its existence from the debris it leaves behind. This reconstruction process is a triumph of experimental design. High-energy collisions produce taus momentarily. Detectors track the paths of decay products, measure energies, and infer where and when the tau existed. Lifetime is not observed directly. It is inferred statistically from millions of events. This distinction matters. At these scales, time is not something seen. It is something extracted from patterns. The tau does not announce how long it lived. Its lifetime emerges from the consistency of its disappearance across many trials. Facilities supported by international collaborations, including laboratories working with ESA member states and data analyzed globally, refined these techniques. The Large Electron-Positron Collider at CERN, operational in the 1980s and 1990s, played a key role by producing large numbers of tau particles. It allowed precise measurement of their decay properties and lifetimes. These experiments confirmed that nature operates comfortably at timescales far beyond intuition. Microseconds, nanoseconds, picoseconds, and femtoseconds are not exotic exceptions. They are routine. What makes this unsettling is not the smallness of the numbers, but their integration into a consistent framework. Particle lifetimes obey the same physical laws as planetary motion and atomic clocks. They fit seamlessly into equations that describe energy, momentum, and interaction strength. The brevity of these lifetimes also reveals something else. Time, at fundamental levels, is probabilistic. A muon does not decay at exactly 2.2 microseconds. That value is an average. Some decay earlier, some later. The same is true for tau particles. Lifetime is not a countdown. It is a probability distribution. This probabilistic nature does not weaken time. It defines it. Quantum mechanics predicts decay rates with extraordinary accuracy, but it does not assign a precise moment to any individual decay. Time at this scale is statistical, not deterministic. This idea was difficult to accept when first introduced. In the early 20th century, many physicists resisted probabilistic descriptions. Albert Einstein himself famously objected to the idea that chance played a fundamental role. Yet, experiments forced acceptance. Particle decays follow probabilities, and those probabilities are confirmed with precision. NASA-supported research into cosmic radiation continues to rely on these principles. Detectors aboard satellites and high-altitude balloons measure particle fluxes and decay products to study astrophysical processes. The timing of these decays, though brief, carries information about energetic events across the universe. Short-lived particles are not confined to laboratories. They are produced in supernovae, around neutron stars, and near black holes. Although telescopes such as the James Webb Space Telescope cannot detect these particles directly, the radiation and signatures they leave behind depend on the same decay processes measured on Earth. This connection bridges scales. The same physics that governs a tau particle's lifetime governs processes occurring in the most extreme environments known. Time at the femtosecond scale influences events spanning millions of years through chains of interaction. As detectors improved, physicists pushed further. In the late 20th and early 21st centuries, experiments began probing lifetimes approaching the femtosecond regime. Some resonances created in high-energy collisions exist for only 10, -15 seconds or less. Their presence is inferred entirely through energy distributions. At this point, language begins to strain. Saying that something exists for a femtosecond risks misleading intuition. Existence here means participation in an interaction. It means contributing to a measurable outcome. It does not mean persistence in the everyday sense. These discoveries reinforce a crucial lesson. Time does not need to be experienced to be meaningful. It does not need duration to feel long. It needs only to be measurable in relation to physical processes. Carl Sagan often emphasized how science extends human senses. Particle physics extends time perception, in the same way telescopes extend vision. It reveals intervals that biology cannot register, but nature uses freely. The existence of short-lived particles also provides a practical benchmark. Long before discussions of Planck time become relevant, physics already operates in regimes where seconds are meaningless. The second, so carefully defined in atomic standards, is far too coarse to describe these processes. This matters because it shows that the breakdown of familiar time units is not hypothetical. It is already routine. The universe has been operating beyond human timescales since its earliest moments, and experiments confirm this daily. As measurements approach ever shorter lifetimes, another pattern emerges. These intervals are still vastly longer than Planck time. Even the briefest particle lifetimes measured are separated from Planck time by many orders of magnitude, and yet, the conceptual shift has already occurred. Time has become something inferred, not counted. This shift prepares the ground for what comes next. If particles can exist for times far shorter than perception, and if time itself stretches and compresses with motion and gravity, then the question becomes sharper. How close have experiments come to the absolute edge of time measurement, where even these statistical methods begin to fail? In the laboratory, ultrafast lasers and attosecond experiments now attempt to track electrons in motion, pushing time resolution toward its final practical limits. Part 5. How close have experiments actually come to the edge of time? Have we already crossed into the shortest moments nature allows, without realizing how close we truly are to the limit? That question does not belong to speculation. It is rooted in laboratories, where time is no longer counted by clocks, but inferred from how electrons move, how photons scatter, and how light interacts with matter over intervals so brief that language itself struggles to keep pace. For most of the 20th century, the smallest measurable times were associated with particle lifetimes. Microseconds and nanoseconds once seemed extreme. Then came picoseconds as electronics improved and detectors sharpened. But a decisive shift occurred when lasers became precise enough to shape light into bursts shorter than the motion they were meant to probe. The femtosecond marked the first major turning point. A femtosecond is 1/millionth of a billionth of a second. At this scale, atoms no longer appear static. Chemical bonds vibrate. Molecules rearrange. Reactions unfold step by step rather than as single events. Chemistry, long described in terms of initial and final states, became a science of motion. This transformation was not abstract. In the 1980s and 1990s, researchers developed techniques using ultrafast laser pulses to initiate and then probe chemical reactions. One pulse would trigger a reaction. Another, delayed by a controlled interval, would record the result. By varying the delay, scientists reconstructed the sequence of events. Time was no longer a background parameter. It became an observable dimension. These methods matured into what is now known as femtochemistry, work that earned Ahmed Zewail the Nobel Prize in 1999. His experiments showed that chemical reactions proceed through intermediate stages, lasting femtoseconds. Bonds stretch before they break. Atoms reposition before stabilizing. These processes were always present. They had simply been too fast to observe. As laser technology advanced, even femtoseconds proved insufficient. Electrons, lighter and faster than nuclei, move on shorter timescales. To follow electron motion within atoms required pulses lasting attoseconds. An attosecond is 1/quintillionth of a second. Light travels less than the width of a few atoms in that time. Generating such pulses required precise control over electromagnetic fields. Researchers shaped laser waves so that their peaks combined to produce isolated bursts of extreme brevity. Facilities supported by international collaboration, including laboratories working with ESA member states and NASA-funded research programs, contributed to this progress. In the early 2000s, the first attosecond pulses were produced and characterized. These pulses allowed scientists to track how electrons respond to electric fields, how they tunnel through potential barriers, and how they redistribute during ionization. Processes once described, statistically, became dynamically visible. Stephen Chu, reflecting on the broader meaning of such experiments, remarked that the goal was not speed for its own sake, but understanding motion by controlling light. His words, "slowing light to understand motion," captured the essence of the approach. By shaping light precisely, researchers could stretch ultra-fast events into sequences that could be analyzed. Attosecond physics did more than push time resolution. It revealed limits. Measuring an interval at this scale does not mean observing time directly. It means inferring time from interaction. The pulse interacts with electrons. The electrons respond. Detectors capture outcomes. Duration is reconstructed from cause and effect mediated by light. This mediation is unavoidable. Light is both the probe and the constraint. The shorter the pulse, the broader its range of energies. At extreme brevity, pulses become disruptive. They alter the systems they measure. This trade-off is fundamental, not technical. Yet the boundary was pushed further still. In 2020, researchers reported measurements approaching the zeptosecond regime. A zeptosecond is 1,000th of an attosecond. These experiments did not involve tracking electrons in atoms. They involved observing how high-energy photons interact with atomic nuclei. Using powerful X-ray pulses, scientists measured the delay between photon absorption and nuclear response. The delays were on the order of a few zeptoseconds. These results represented the shortest directly inferred times ever measured. Even here, the method remained indirect. No device ticks every zeptosecond. Instead, physicists analyzed energy distributions, angular correlations, and interaction patterns. Time was encoded in structure. These achievements might suggest that experiments are approaching a fundamental edge, but the numbers tell a different story. A zeptosecond is still vastly larger than Planck time. The gap between them is not incremental. It is enormous. Planck time is approximately 5.39 times 10, negative 44 seconds. The difference between a zeptosecond and Planck time spans more than 20 orders of magnitude. No foreseeable experiment bridges that distance. This disparity matters because it clarifies what experimental progress represents. Each advance reveals new layers of motion. None imply proximity to the ultimate limit. Ultrafast experiments explore the dynamics of matter and radiation within known physics. Planck time belongs to a regime where space-time itself becomes unstable. NASA and ESA research programs continue to support ultrafast science because it connects laboratory physics with astrophysical processes. In extreme environments, such as accretion disks around black holes or the aftermath of supernovae, particles interact on ultra-short timescales. While telescopes like the James Webb Space Telescope cannot observe these times directly, the radiation they detect carries signatures shaped by ultra-fast interactions. JWST observations of ionized gases, star-forming regions, and energetic outflows depend on atomic and electronic processes that occur on femtosecond and attosecond scales. Understanding these processes improves interpretation of astronomical data. Time at the smallest accessible scales informs structures spanning light years. Despite these connections, experimental limits remain clear. As pulses shorten, energy spreads. As resolution increases, disturbance grows. At some point, probing an interval alters the phenomenon irreversibly. This is not a failure of engineering. It is a property of nature. Physicists recognize this as a practical horizon, not the edge of time itself, but the edge of experimental access. Beyond it, description requires new principles. Carl Sagan often emphasized how scientific progress reshapes perspective. Ultrafast physics does exactly that. It reveals that what once seemed instantaneous contains structure. What once appeared static is in constant motion. Yet, it also reveals restraint. Nature allows extraordinary access, but not infinite resolution. The experiments closest to the edge of time teach humility through precision. They show how far measurement can go, and how clearly it must stop. The universe does not conceal this boundary. It enforces it quietly, through trade-offs that no technique escapes. What emerges is a layered picture. Human perception operates on seconds. Technology refines this to microseconds and beyond. Physics pushes into attoseconds and zeptoseconds, and then the trail fades. Not because curiosity ends, but because the framework itself changes. Even as experiments reach astonishingly small intervals, they remain unimaginably distant from Planck time, a scale that is not simply shorter than anything measured before, but different in kind. Part 6. Why is Planck time not just shorter, but fundamentally different? What turns Planck time into a wall, rather than simply the next smaller step, is not its size, but the way physics itself changes when that scale is reached. Up to now, every shortening of time has revealed more detail, more structure, more motion. But at Planck time, shortening no longer clarifies. It destabilizes the very framework used to describe anything at all. To see why, it helps to notice how all previous time intervals were reached. Microseconds, femtoseconds, attoseconds, even zeptoseconds were discovered through experiments. They were measured by observing particles, fields, and interactions. Each interval existed because something physical persisted long enough to leave a trace. Time was inferred from change. Planck time is different from the start. It is not measured, it is derived. It emerges from combining three constants that appear repeatedly in modern physics. The speed of light sets the maximum rate at which information can travel. Planck's constant sets the scale at which quantum effects become unavoidable. The gravitational constant sets the strength with which energy curves space-time. None of these constants depend on clocks or observers. They describe how the universe behaves regardless of measurement technique. When these three constants are combined, they produce a timescale that does not describe how long something lasts. It describes the point at which existing descriptions stop working together. Quantum mechanics governs small scales with remarkable accuracy. It explains atomic structure, particle interactions, and decay processes. General relativity governs large scales with equal success. It explains planetary motion, black holes, gravitational waves, and the expansion of the universe. Each theory has been confirmed repeatedly by observation, including data from NASA missions, ESA observatories, and ground-based detectors such as LIGO and Virgo. The difficulty appears only when both theories are required simultaneously. At the Planck scale, energies become so concentrated over such short durations that quantum uncertainty and gravitational curvature can no longer be separated. Attempts to describe one immediately disrupt the other. This is not a technical inconvenience. It is structural. Any effort to localize an event to intervals shorter than Planck time requires concentrating energy into a region so small that space-time itself would be strongly curved. According to general relativity, that curvature would collapse into a microscopic black hole. The act of measurement destroys the possibility of measurement. This reasoning does not rely on speculation. It follows directly from established equations. Physicists do not argue about whether this effect exists. They argue about how to describe what replaces smooth spacetime at that scale. John Wheeler gave this problem a memorable name when he spoke of spacetime dissolving into what he called quantum foam. He did not mean foam in a visual sense. He meant a regime where geometry itself fluctuates violently, where distances and durations cannot be assigned stable values. Below the Planck scale, space-time can no longer be treated as a continuous background. The assumptions that allow clocks to tick, rulers to measure, and events to be ordered cease to apply. Time does not become shorter. It becomes undefined in the usual sense. This distinguishes Planck time from every interval discussed so far. Attoseconds and zeptoseconds are extreme, but they are still part of a continuous timeline. They belong to physics as it is practiced today. Planck time marks the boundary of that practice. The history of physics shows how seriously this boundary is taken. Since the mid-20th century, researchers have sought a theory of quantum gravity precisely because of this conflict. Loop quantum gravity, string theory, and other approaches all begin with the same recognition. Classical spacetime cannot survive unchanged at the Planck scale. In loop quantum gravity, spacetime is proposed to have a discrete structure. Areas and volumes come in smallest possible units. Time evolution proceeds through transitions between these states, not through smooth flow. In this view, Planck time represents the minimum meaningful update between states. In string theory, fundamental objects are not points, but extended structures. Their vibrations define particles. Space-time geometry emerges from deeper degrees of freedom. Planck time marks the scale at which these underlying structures dominate, and familiar notions of distance and duration lose autonomy. Despite their differences, these approaches agree on one thing. Planck time is not accessible by refining existing experiments. It requires new principles. Observational cosmology provides indirect motivation for this conclusion. Data from the cosmic microwave background, measured with high precision by the Planck satellite, show that the early universe was remarkably uniform, yet seeded with tiny fluctuations. These fluctuations are consistent with quantum processes operating in a rapidly expanding spacetime. The earliest moments of the universe, often referred to as the Planck epoch, lie beyond direct observation. However, their influence is encoded in large-scale structure, galaxy distributions, gravitational wave backgrounds, and temperature anisotropies, all carry imprints shaped by physics near this boundary. The James Webb Space Telescope has begun to observe galaxies forming earlier than many models anticipated. While JWST does not probe Planck-scale physics directly, its findings sharpen the need for theories that connect quantum processes with space-time evolution from the very beginning. What makes Planck time particularly unsettling is that it cannot be bypassed by clever design. Ultra-fast lasers approach zeptoseconds by controlling electromagnetic fields. Particle accelerators infer femtosecond lifetimes by reconstructing decay products. None of these methods approach the Planck scale because the obstacle is not speed, it is consistency. At intervals near Planck time, the concept of cause preceding effect becomes ambiguous. Light cones, which define causal structure, fluctuate. Without a stable space-time background, the ordering of events cannot be defined unambiguously. This does not imply chaos. It implies that the familiar language of physics must change. Time, as used in equations, must be replaced or reinterpreted. Physicists are careful about how they describe this. They do not claim that the universe behaves irrationally at the Planck scale. They claim that current theories are incomplete there. Carl Sagan often emphasized how boundaries in science mark opportunities rather than failures. He wrote, "Somewhere, something incredible is waiting to be known." In this case, what waits is not a smaller clock, but a deeper framework. Planck time is therefore not an experimental target. It is a consistency check. Any theory that claims to describe reality at all scales must explain why spacetime appears smooth above this boundary, and why it cannot be extended below it. This also explains why Planck time appears repeatedly in discussions of the origin of the universe. During the earliest moments after the Big Bang, densities and energies approached Planck values. Classical descriptions of expansion cease to apply. Inflationary models, quantum cosmology, and proposals such as bouncing universes all confront this boundary. The distinction between shorter and fundamentally different becomes clear here. Shorter intervals still belong to time as a parameter. Planck time signals the breakdown of time as a parameter. Nothing measured so far contradicts this picture. Every experiment confirms that physics behaves smoothly well above the Planck scale and refuses to yield predictions below it. This consistency across theory and observation gives Planck time its authority. As this realization settles, the focus shifts naturally. If Planck time marks a boundary where space-time itself becomes unstable, then the next question concerns what existed before space-time behaved as we understand it now, and whether concepts such as before and after can survive at all in that regime. At the very beginning of the universe, the familiar order of before and after may already fail, making it unclear whether time itself can be said to exist at all. Part 7. Did space and time even exist before the first Planck time? What if asking what came before the universe is already a question that physics cannot meaningfully answer? At the earliest boundary we can describe, time itself may not yet function, and space may not yet exist in any form we would recognize. This boundary is known as the Planck epoch, the earliest interval in the history of the universe, for which our physical theories can even attempt description. It begins at the first meaningful moment after the Big Bang, around 5.39 × 10 -44 seconds, the Planck time. Anything earlier lies beyond the reach of equations that have otherwise proven extraordinarily successful. To understand why this matters, it helps to recall how cosmology normally works. Modern models of the universe are built by running the equations of general relativity backward in time. As we reverse cosmic expansion, matter becomes denser, temperatures rise, and distances shrink. This method has worked remarkably well. It explains the cosmic microwave background observed by NASA and ESA missions, the abundance of light elements, and the large-scale structure of galaxies seen by telescopes, including the James Webb Space Telescope. But when these equations are pushed all the way back to the beginning, something unusual happens. They stop producing meaningful answers. As the clock approaches the Planck time, energy densities grow so large that quantum effects can no longer be ignored. At the same time, space-time curvature becomes extreme. The assumptions that allow general relativity to describe smooth geometry break down, and quantum mechanics lacks a way to describe space-time itself. The two frameworks collide. Physicists do not describe this collision as a failure of mathematics. They describe it as a signal. It marks the limit where familiar concepts no longer apply. During the Planck epoch, the universe is thought to be incredibly hot and dense, far beyond the conditions reproduced in any laboratory or astrophysical environment we can observe today. Distances smaller than the Planck length lose operational meaning. Durations shorter than Planck time cannot be ordered consistently. Space and time, as separate entities, no longer function as a stable background. This is why the question of what existed before Planck time is problematic. The word before assumes an ordering in time, but time itself may not yet be defined in a way that allows such ordering. Alan Guth, one of the architects of cosmic inflation theory, has repeatedly emphasized caution here. The early universe, he notes, demands humility. Concepts that work well later may not apply at the beginning. Inflationary models describe rapid expansion shortly after the Planck epoch, not because physics refuses to look earlier, but because current theories cannot justify going further back. Observational evidence supports this restraint. The cosmic microwave background, mapped with extraordinary precision by the Planck satellite, shows that the universe was already expanding smoothly when it became transparent to radiation about 380,000 years after the Big Bang. The patterns in that radiation encode information from even earlier times, but not from the Planck epoch itself. What we see is indirect. Temperature fluctuations reflect quantum processes stretched by inflation. They hint at physics near the Planck scale, but they do not reveal it directly. The James Webb Space Telescope extends this picture further by observing galaxies forming surprisingly early in cosmic history. Some galaxies appear massive and structured at times when models predicted more gradual development. These observations do not rewrite the Planck epoch, but they sharpen the urgency of understanding how space-time emerged from earlier conditions. In theoretical work, several approaches attempt to describe this emergence. In some models of quantum cosmology, space-time itself is not fundamental. It arises from more basic elements, such as quantum states or relational structures. Time, in these views, is not a background parameter, but an emergent property tied to change. Other models suggest that the Big Bang was not a beginning but a transition. In bouncing cosmologies, a contracting universe reaches extreme density and then rebounds into expansion. In such scenarios, Planck-scale physics governs the transition, and classical time loses continuity across it. Asking what happened before becomes ambiguous, because the arrow of time may reverse or reset. Despite their differences, these models share a core message. At the Planck epoch, space-time as we know it does not yet exist. The familiar grid of distances and durations emerges only afterward. This conclusion is not philosophical. It is grounded in how physical descriptions work. Measurements require clocks and rulers. Clocks require stable intervals. Rulers require stable distances. At Planck scales, neither stability exists. NASA-supported research into early universe physics continues to explore these questions indirectly through gravitational waves, high-energy astrophysics, and precision cosmology. Future detectors may probe primordial gravitational waves that carry information from epochs earlier than the cosmic microwave background. Even then, interpretation will rely on assumptions about how space-time behaves near the Planck scale. What physics currently offers is not a picture of a universe emerging into pre-existing space and time, It offers a picture of space and time emerging together. This reframes the Big Bang. It was not an explosion in space. It was the appearance of space itself. It was not an event that happened at a time. It was the origin of time as a meaningful parameter. Carl Sagan often reminded audiences that science advances by knowing where explanations end. He once said, "We are like butterflies who flutter for a day and think it is forever." In cosmology, this humility is essential. The Planck epoch is not a failure of imagination. It is a boundary of description. The deeper lesson is subtle. Physics does not say that nothing existed before Planck time. It says that the concepts used to describe existence are not yet defined. As the universe expanded and cooled past this epoch, space-time stabilized. Distances became measurable. Durations became comparable. Cause and effect gained structure. Only then did the familiar flow of time begin. At energies far beyond those of the present universe, space-time may not yet exist as a stable backdrop, and the forces we now distinguish could have been indistinguishable from one another. Part 8. Were all forces once a single force at the dawn of the universe? What simplicity could possibly lie beneath the tangled complexity of the forces that govern everything we see today? That question does not arise from imagination. It arises from patterns hidden inside the equations that describe nature, patterns that suggest the universe may have begun with fewer rules than it now obeys. In the world we experience, 4 fundamental interactions shape all physical processes. Gravity governs the motion of planets and galaxies. Electromagnetism binds atoms, produces light, and powers technology. The strong nuclear force holds atomic nuclei together. The weak nuclear force governs radioactive decay and particle transformation. They appear distinct, each with its own strength, range, and behavior. But this separation may be a late development in cosmic history. The idea that forces might unify at high energies emerged gradually in the 20th century. It was not introduced as a philosophical preference, but as a response to experimental results. In the 1960s, physicists studying particle interactions noticed something unexpected. When equations describing the electromagnetic force and the weak nuclear force were examined at higher energies, their strengths began to converge. This convergence was not guessed, it was calculated. Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that electromagnetism and the weak force could be described as 2 aspects of a single framework, now known as the electroweak theory. At everyday energies, these forces appear different. At sufficiently high energies, they merge into one. This prediction was later confirmed experimentally. In the 1980s, experiments at CERN observed particles called W and Z bosons, exactly as electroweak theory predicted. What once seemed like 2 separate forces were revealed to be manifestations of a deeper unity. This success changed how physicists thought about forces. If 2 forces could unify, why not more? The strong nuclear force soon entered the discussion. Theories known as grand unified theories proposed that at even higher energies, the strong force might merge with the electroweak interaction. In these models, the 3 non-gravitational forces become one. Evidence for this unification remains indirect, but the mathematical structure is compelling. Calculations show that when the strengths of these forces are extrapolated to extremely high energies, close to those present in the early universe, they nearly converge. The convergence is not perfect, but it is suggestive. Gravity complicates the picture. It is vastly weaker than the other forces at accessible energies, yet gravity governs space-time itself, and its influence grows as energy density increases. Near the Planck scale, gravity cannot be ignored. Any attempt to describe the earliest universe must include it. This is where the idea of full unification emerges. Under Planck scale conditions, when energies are extreme and space-time itself fluctuates, gravity may merge with the other forces. The universe, at its beginning, may have been governed by a single interaction. This proposal is not confirmed, but it is not arbitrary. It follows from how physical laws behave under extreme conditions. Cosmology provides indirect support. As the universe expanded and cooled, it passed through a series of transitions. Each transition broke a symmetry, separating forces that were once unified. This process is known as symmetry breaking. A familiar analogy comes from condensed matter physics. When water cools and freezes, it transitions from a symmetric liquid state to a structured solid. The underlying laws remain the same, but the system settles into a less symmetric configuration. In the early universe, similar transitions may have occurred, but with forces rather than molecules. During these transitions, the universe did not merely change temperature, it changed its rulebook. At the highest energies, near the Planck epoch, distinctions between forces may not have existed. As the universe cooled, gravity separated first. Later, the strong force separated from the electroweak interaction. Finally, electromagnetism and the weak force separated, producing the world we now observe. Observational cosmology supports this staged picture indirectly. Measurements of the cosmic microwave background by NASA and ESA missions reveal a universe that was once extremely uniform. Tiny fluctuations in temperature and density seeded the formation of galaxies. These fluctuations are consistent with a universe governed by simple, symmetric laws early on. The James Webb Space Telescope extends this story by observing galaxies forming rapidly and efficiently in the early universe. While JWST does not observe force unification directly, its data constrain how quickly structure emerged after symmetry breaking. These observations inform models of early universe physics and the conditions under which forces differentiated. Particle physics experiments also contribute. Facilities such as CERN test force behavior at the highest energies achievable on Earth. Although these energies remain far below those of the early universe, they allow physicists to verify how force strengths evolve with energy. Each confirmation strengthens the case that unification is not merely aesthetic, but grounded in measurable trends. American physicists played a central role in developing these ideas. From the formulation of electroweak theory to ongoing research in quantum gravity, the pursuit of unification has been driven by the desire to explain complexity through simplicity. Yet caution remains essential. No experiment has directly observed full force unification. Gravity remains stubbornly resistant to quantum description. Attempts to unify it with other forces lead to mathematical challenges that have not yet been resolved. String theory offers one possible framework. In string theory, particles are not points, but vibrating strings. Different vibrations correspond to different particles and forces. Gravity emerges naturally within this framework. Under this view, unification is not imposed. It arises from geometry at the smallest scales. Loop quantum gravity takes a different approach, focusing on quantizing space-time itself. In this framework, forces interact within a discrete space-time structure. Whether unification emerges in the same way remains an open question. Despite these differences, all serious approaches agree on one point. The early universe operated under conditions radically different from those we observe today. Forces behaved differently. Symmetries were higher. The laws we now experience are remnants of a simpler origin. This does not mean the universe began in chaos. It suggests the opposite. It began in a state of remarkable simplicity. Carl Sagan often emphasized that science seeks hidden order beneath apparent complexity. The unification of forces embodies this idea. What appears fragmented now may once have been whole. As the universe expanded and cooled, that unity fractured. Gravity shaped space-time. The strong force bound nuclei. Electromagnetism lit the cosmos. The weak force governed transformation. Each took on a distinct role. But the possibility remains that these roles emerged from a single interaction, operating under conditions no longer accessible. Understanding this origin is not about nostalgia for simplicity. It is about completeness. A unified description would explain not only why forces differ today, but why they exist at all. This pursuit continues through theory, experiment, and observation. Each new measurement refines the picture. Each constraint narrows the possibilities. And as this picture sharpens, another issue comes into focus. If forces were once unified, then the properties of particles themselves may also have been different. Mass, charge, and identity may not have been fixed at the beginning, when the scale of Planck time is set beside the scale of the entire universe. The earliest moment stands out as an interval so small that ordinary intuition about time and size no longer applies. Part 9. How extreme is Planck time compared to anything we can imagine? How many distinct moments could exist inside a single second before the idea of a moment itself loses meaning? The answer is not merely large. It is so far beyond everyday comparison that intuition stops being useful, and only scale remains. To begin grounding this, consider the age of the universe. Observations from NASA, ESA, and multiple independent cosmological probes converge on a consistent value. The universe is about 13.8 billion years old. Converted into seconds, that corresponds to roughly 4.35 times 10, 17 seconds. This number already exceeds direct human comprehension, but it remains finite, measurable, and tied to observable evidence, such as cosmic expansion, stellar evolution, and the cosmic microwave background. Now compare that entire span to a single second. 1 second contains about 10 to the power of 43 Planck times. That is not an exaggeration or a poetic flourish. It is a direct consequence of the definition of Planck time, approximately 5.39 times 10, negative 44 seconds. This comparison reveals something essential. Planck time is not simply small. It belongs to a different category of scale. To appreciate how extreme this is, reverse the comparison. If 1 Planck time was stretched to last 1 second, then 1 real second would expand to more than 10 to the power of 35 years. That duration is vastly longer than the current age of the universe, longer than the projected lifetimes of stars, longer than any astrophysical process we know how to model. The difference is not additive, it is exponential. Astronomy routinely deals with large numbers, but even within that context, Planck time stands apart. Distances between galaxies are immense, yet they can be expressed in light years. Stellar lifetimes span billions of years, yet they follow well-understood sequences. Planck time does not sit at the small end of a familiar spectrum. It marks a transition where scale itself behaves differently. This distinction becomes clearer when comparisons are made carefully. A nanosecond is to a second what a second is to about 30 years. A picosecond is to a second what a second is to 30,000 years. A femtosecond corresponds to about 30 million years. An attosecond corresponds to nearly 30 billion years, roughly twice the age of the universe. Each step compresses intuition further, but Planck time goes far beyond this progression. It does not correspond to another historical era. It surpasses the entire cosmic timeline many times over. This matters because physical laws behave differently across scales. At human scales, time appears smooth. At atomic scales, time becomes quantized through interactions. At particle scales, time becomes probabilistic. At Planck scales, time ceases to function as a parameter within known physics. Observations reinforce this layered picture. The James Webb Space Telescope reveals galaxies forming within the first few 100 million years after the Big Bang. Those galaxies contain stars, heavy elements, and complex structures. All of that complexity emerged within a time span that dwarfs Planck time beyond comparison. Even the inflationary epoch, thought to have occurred shortly after the Big Bang, lasted far longer than Planck time. Inflation models describe rapid expansion over intervals many orders of magnitude longer. Planck time sits beneath all of this, as a boundary, not as a participant in cosmic evolution, as we can currently describe it. This extreme separation explains why Planck time cannot be approached experimentally. Ultrafast lasers reach zeptoseconds. Particle lifetimes reach femtoseconds and beyond. These are impressive achievements, but they remain astronomically distant from the Planck scale. The gap is not one of technological limitation alone. It reflects a change in what it means to measure time. Measurement depends on change. Change depends on interaction. Interaction depends on space-time structure. At Planck time, space-time itself becomes unstable, according to current understanding. The foundation required to define duration dissolves. Cosmology offers another perspective. The earliest moment that physics can meaningfully describe is the end of the Planck epoch. At that point, the universe had already expanded beyond Planck scales. Time had acquired enough structure to allow ordering of events. Only then could processes such as inflation, particle creation, and symmetry breaking unfold. Everything observed today traces back to moments after this transition. The cosmic microwave background, measured by missions such as COBE, WMAP, and Planck, carries information from hundreds of thousands of years later. Gravitational waves detected by LIGO carry information from violent astrophysical events billions of years later. None of these signals reach back to Planck time itself. This absence is not accidental. It reflects the fact that Planck time does not behave like a conventional interval. It is not a slice of history waiting to be observed. It is a limit beyond which history, as we define it, does not extend. Physicists emphasize this carefully. Planck time does not imply that the universe flickers in discrete ticks of that duration. There is no evidence that time advances in Planck-sized steps. Instead, Planck time marks the scale at which the notion of continuous progression loses theoretical support. This distinction is often misunderstood. Comparing Planck time to everyday intervals is useful only to highlight its extremity, not to suggest that reality operates like a digital clock. Current theories do not require time to be discrete. They require that classical descriptions fail far above that limit. The extreme nature of Planck time also reshapes how scale is taught and discussed. Human intuition evolved to handle seconds, minutes, and years. Even millions of years can be grasped through analogy. Planck time resists analogy because it does not correspond to any familiar process. Carl Sagan often emphasized scale as a tool for understanding the universe. He reminded audiences that perspective changes meaning. In the case of Planck time, perspective alone is insufficient. Scale itself becomes the message. This is why Planck time is described as a categorical boundary rather than a small number. It divides regimes of physics. Above it, space-time behaves as a smooth arena where fields and particles interact. Below it, space-time cannot be treated as a stable background. No observation contradicts this picture. Every successful prediction in physics operates comfortably above this scale. Every attempt to push theory below it encounters inconsistency. The agreement between theory and observation across so many orders of magnitude gives this boundary its credibility. The extremity of Planck time also reframes how we think about the universe's beginning. The Big Bang was not a moment in time preceded by other moments. It was the emergence of time as a usable concept. Planck time marks the smallest interval after which time can be meaningfully discussed. Seen this way, Planck time is not about smallness. It is about limitation. It tells us where description ends, not where existence begins. As this perspective settles, another realization becomes unavoidable. If Planck time is traversed constantly as the universe evolves, and yet remains forever inaccessible to experience or measurement, then the continuity we perceive must arise from averaging over unimaginable numbers of these intervals. Even if reality unfolds through Planck scale intervals, the time we experience remains smooth and continuous, suggesting that whatever governs those smallest scales is not accessed directly by perception or by any ordinary clock. Part 10. If we pass through Planck time constantly, why can't we ever feel it? What if, at this very moment, every movement you make is crossing the smallest intervals time allows? Again and again, without leaving the slightest trace in awareness? That possibility is not poetic. It follows directly from how physics and biology handle time at radically different scales. From the perspective of fundamental physics, nothing moves smoothly. Every physical process unfolds through interactions governed by quantum laws and constrained by relativity. If Planck time represents a boundary where space-time itself changes character, then any motion that persists over a measurable duration must, in principle, span an enormous number of these intervals. A single second contains on the order of 10 to the power of 43 Planck times. That number is not symbolic. It is a direct consequence of the constants measured in laboratories and confirmed across cosmology. Yet none of this is felt. No flicker, no granularity, no sense of stepping across microscopic thresholds. The reason begins not with physics, but with physiology. Human perception of time is built from biological processes that are slow by cosmic standards. Neurons transmit electrical signals on the order of milliseconds. Chemical processes at synapses unfold over comparable durations. Reaction times measured in neuroscience experiments typically range from a few hundred milliseconds to a second, even under extreme conditions. The brain does not register events separated by less than a few milliseconds as distinct. This is not a limitation of attention. It is a structural property of neural systems. Studies in sensory neuroscience show that visual perception integrates information over short time windows. Sounds arriving within tens of milliseconds are fused into a single auditory event. Motion appears continuous because the brain averages change across intervals vastly larger than any fundamental physical scale. Time, as experienced, is already a smoothed signal. This averaging begins far below conscious awareness. Photoreceptor cells in the retina respond to light with chemical cascades that take milliseconds to complete. Muscles contract through biochemical cycles that last even longer. At every stage, information is integrated, filtered, and delayed. From this perspective, Planck time is not merely too small to notice, it is too small to participate. Physics reinforces this conclusion. There is no known mechanism by which Planck's scale structure could imprint itself directly on biological systems. The energies associated with Planck scale phenomena are far beyond those present in chemical or neural processes. Even the most sensitive detectors built by humans cannot resolve such intervals, not because they lack refinement, but because resolving them would require conditions that disrupt space-time itself. This is why physicists are careful when discussing Planck time. They do not describe it as a ticking clock beneath reality. They describe it as a limit of description. Current theories do not require time to advance in discrete Planck-sized steps. They require that classical space-time loses meaning below that scale. The continuity you experience does not contradict Planck time. It emerges from averaging over immense numbers of microscopic interactions. A useful comparison comes from thermodynamics. Temperature feels smooth, yet it arises from the motion of countless particles. Individual molecular collisions are not felt. Only the collective average registers as warmth or cold. Time perception operates in a similar way. Individual quantum events are not experienced. Only aggregated change becomes duration. Modern physics supports this layered view. Quantum mechanics governs microscopic behavior. Statistical mechanics governs large ensembles. Relativity governs space-time structure. Each layer remains valid within its domain. None require human sensation to track fundamental scales. NASA-supported research in neuroscience and human physiology confirms this separation. Studies of circadian rhythms, reaction times, and temporal perception show that human experience of time is shaped by biological clocks tuned to environmental cycles, such as day and night, not to fundamental physics. At the same time, physics demonstrates that motion proceeds independently of perception. Satellites orbit Earth, guided by equations that account for relativistic time dilation. Atomic clocks drift relative to one another depending on altitude and velocity. These effects are real, measurable, and invisible to direct sensation. The same applies to Planck time. If it plays a role in the underlying structure of space-time, that role is entirely hidden beneath layers of averaging. This helps resolve a common misunderstanding. Saying that every motion traverses Planck time does not mean that time advances through discrete units like frames in a film. There is no experimental evidence for such discreteness. Instead, it means that if there is a smallest meaningful interval, then all longer durations are composed of physics operating above that boundary. The distinction matters. Planck time does not interrupt continuity. It limits resolution. Carl Sagan often spoke about how science reveals layers beneath everyday experience. He reminded audiences that we are a way for the cosmos to know itself. That statement applies here, in a precise sense. Human awareness samples reality at scales suited to survival, not to fundamental description. Physics extends perception, but only through instruments and inference. The fact that Planck time cannot be felt is therefore not surprising. It is expected. What is more remarkable is that despite this separation, descriptions across scales remain consistent. Equations governing subatomic particles align with observations of galaxies billions of light-years away. The same constants that define Planck time also shape stellar evolution and cosmic expansion. This coherence allows physicists to trust boundaries, even when they cannot be crossed. Planck time marks where known descriptions stop. It does not demand that experience reflect that limit. The smoothness of time, then, is not evidence against Planck time. It is evidence of how effectively nature averages complexity into stability. As the universe evolves, it carries forward this averaging. From the earliest moments after the Planck epoch, space-time expanded and cooled. Interactions slowed. Structures formed. Time became something that could be measured, compared, and eventually experienced. Human life occupies a narrow band within this vast spectrum. Seconds matter, minutes matter, years matter. Planck time does not. And that is not a deficiency. It is a clue. It tells us that understanding does not require direct sensation. It requires consistency between theory and observation. Planck time survives because nothing observed contradicts it, and because it resolves conflicts between the deepest theories we have. As this journey closes, the picture that remains is clear. Time feels continuous because biological systems integrate change. Physics describes deeper structure without requiring experience to match it. The two views coexist without conflict. Carl Sagan once wrote, "Somewhere, something incredible is waiting to be known." In this case, what waits is not a sensation, but a framework. A way to reconcile gravity, quantum mechanics, and space-time into a single account. Until then, Planck time remains what it has always been. Not a beat we can hear, not a moment we can feel, but a boundary that quietly shapes the universe beneath every second we live through. Thank you for spending this time here. As the lights grow softer and the day settles, may these ideas rest easily with you. Wherever you are listening from, may the night carry you calmly forward, and may your rest be deep and untroubled. I wish you a good night's sleep and a peaceful night.